So we have our example. Any questions? It's just on the thermodynamics, it's not any of this stuff. Okay. So we started looking at a positive, so we had the definition of electric field. What's the formal definition of electric field? Yes, the force that the charged object exerts on the little q, so the object here, on the q, this q is your test charge. Okay. The object is whatever you put electric charge on. And this force is your electric force. It's just not any force, it's only the electric force. We divide it by the test charge Q, like this. So that's the formal definition of electric field. Okay? Now, what can we do with this? We said we want to start drawing these pictures. So we took a point charge. We like to be positive, so that's a little positive test charge. And so how did we, so I'll call this Q. So how did we then find the electric field? Well, we put our little test charge here, Q. We looked at the force that this charge exerts on this one, and it's like this. So this is a force that Q exerts on little q. If I want the electric field, then I divide that by Q, and I'm going to get something that goes like this. That would be my electric field at that point. So how do I get it at all the other points? You just put your little test charge there, you measure the force divided by Q, and then that would be then the electric field here. And I'd have one then here as well. And put this at every single point. Now what did we say happens? Instead of here's a positive charge, if I look along here, the electric field at this spot is like this. What's the electric field at this spot? Yeah, it's not going to be as great, so it's going to go like this. Then if I go a little bit further away, it goes like this. And further away, it goes like this. It keeps on getting smaller and smaller and smaller the further away you go. The same is true in any other direction. So I have this one here, 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 and so on and so forth. Okay, this would take forever to draw a picture like this if you had to keep on doing this. And so Michael Faraday came up with a way of actually basically drawing these electric field lines, but making it a lot easier to draw. So what I'm going to give you are basically Michael Faraday's rules for drawing electric fields. So to make drawing E lines easier, okay, we follow Michael Faraday's rules for drawing in lines. Okay, so this is what we're going to do. So to begin with, okay, E line, draw continuous E lines. So now here where I draw a line, I have a break, draw a line, break, line, break, line, break. You don't do that at all. So what you're going to do in this case here would be your positive charge here like this. You just have a straight line like that. That would be the E line here. And if I had one going down like this would be an E line like this. If I had one like this would be an E line like this, like this, like this. This is what you draw. Okay, so they're continuous. Now, you realize something. Why did we draw this arrow bigger and then this arrow smaller?
The force is not as much as it is towards the end as it is.
Yeah, there's a bigger force here. There's a smaller force here. Well, Michael Faraday realized that if you just draw continuous lines like this, what happens? If I'm right here, these E lines are really close together. If these E lines are close together, you have a strong E field. If But if I look over here, the distance between these E lines are bigger. If those E lines are further apart, it's weaker. So just by drawing lines like this, you automatically have this information about the strength already in the picture. So what happens here is that when the lines are further apart, the E field is weaker. If you look over here, kind of in this distance here, where they're closer together, where the lines are closer together, the E field is stronger. So that's kind of neat. Next point, the number of E lines is proportional to how much charge you have. The number of E lines is directly proportional to the amount of charge. What does this mean? So let's say I had a Q here. This is plus Q. Let's say this is plus 3Q. Actually, that's going to be hard to do. I'll just say 2Q. So let's say I'm over here and I draw 4 lines like this. So I just happen to draw 4 lines over here for this one. How many E lines should I draw over here? If I double the charge, I'd have to have 8 E lines. So I have this. 1, 2, 3, 4, 5, 6, 7, 8. Yes?
Is that how we notate how much charge there is? Like we just put 2, so it's like it's double now?
Yeah, that's one way to do it. Sometimes I can just give you a value. So I can say this is 2 microcoulombs and then this is 4 microcoulombs. That'd be another way. This way here, I'm just kind of doing it general. So the number of lines is proportional to the amount of charge. Okay? The third point. E lines go, start, E lines start at positive charges. And terminate at negative charges or infinity. So let me kind of explain why this one works. Okay, let's ask, so there's a reason for this. Let's ask, how do E lines look for negative charges? So if I had a negative point charge, this is a negative Q, how would those E lines have to go? Remember, we said if we put the positive charge here, that force is going this way? So these would have E lines going in it. So this would have something like this. That's what they'd have to adhere. Okay? So that's why they're going to stop at a negative charge. Now, if we had a positive and a negative, let's say I had a positive charge and a negative charge. Okay, what would this look like? If I had an E line going out like this, going this way, where would that line have to stop? That line would keep on going all the way to infinity, and just keep on going on to infinity like this, and never stop. Suppose I have an E line going this way. Where would it stop? At the Q. Okay. We're going to have some going out like this, but don't worry about those yet. We're going to figure out what's going to happen. Now, what about, let's say I'm drawing this one. What would be the corresponding line of this and this line? It would be a line coming from infinity and then terminating on that negative charge. So if I just look along this x-axis here, that's how I draw those lines. I'll show you what to do over in these regions in just a second. Okay? So the E lines start at positive charges, right? So they go away from positive charges, and then they terminate going into here. So by this, I mean the lines, the E lines, go from positive charges and into negative charges. So you can never have something like this. Here's a negative Q. You can never have this. E lines don't come out of negative Qs. They go into negative Qs. Okay?
I guess my only confusion is like I thought like opposite charges were supposed to attract, and I see
They do.
attract over there, but like that plus going to the left, is it just right?
That's the E field.
Oh, okay.
That's the E field.
Okay.
Okay? Now, fourth one. The fourth one I'm not going to prove. I will give you a proof later on, but right now the proof would make no sense. Okay? E lines never cross. I'll say proof later. Meaning what? You can't have an E line, like this can't be some E line E1, and this can't be some E line E2. You can't have that. That's not allowed. They never cross. So the problem is, then what on earth happens with this? So we could say, well, what about our friend over here? Let's say what? This one. So how do we say the electric field looks here? The electric field for this guy goes this way. How does it go for this one? Into it. That's not what you have. And this doesn't exactly happen. Okay, what do you think instead happens? So, not allowed. You can kind of guess. If you had two vectors and if you add them together, what do? How do vectors add? So if I mark here, I have this vector here, I have that vector here. How do those vectors add? People who've had first semester physics?
Tip to tail.
They're doing a tip to tail fashion. So you'd actually have something like, you'd put this over here, and you'd actually have that guy here. So what this is going to really look like is when you do this all together. You know, this guy go like this. What do you think about one going like this? That's going to go into here. How do you think it's going to look? It's going to go like this. And if I have one that goes up like this, it's going to go like this. And one like this, this, that, this, and then you have one here going way, way up here and going in like this. Same way with this guy here. And that guy going out all the way to infinity, and this going out all the way in front of me. That's how the electric field would look for a positive and negative charge. Okay. Questions? Make sense? Yes.
Yeah. Makes sense.
Okay, you look like you have a question.
I'm just thinking.
Okay.
Is all. I think I got it.
What would this be then? Now, the nice thing about this, what does it look like these two charges are doing from that picture? You know, this looks like these are attracting, and they are. Yes.
Are those lines supposed to be straight?
Which lines?
The ones at the.
No, these would eventually curve. This one will be straight
Okay.
because it's going just like this. This one would ultimately curve up and then come down here like this one. What about this? Let's add a positive charge and a positive charge. How's that one going to look?
I mean, it's just gonna repel. There wouldn't be like a line in between them.
Okay, so what you're going to have, these are going to look like these are going to repel. What this is going to look like, this is going to look like this. That's what that looked like. And you can see that. What's the electric field at the center here? There wouldn't be one. This kind of showed you that. Okay. And what does it look like these are doing? It looks like two things repelling. Okay. So these Z lines here, when you draw them, it really kind of gives you a very visual way of looking at how the system is going to look. Questions? Now, we're going to have more, we're going to eventually start putting charge on a metal object, and we're going to find out about metal objects and stuff like this. But this is, there's going to be more rules we're going to get, but not quite yet. Okay? Let's do a couple of little calculations. Let's ask, how can we calculate E fields? So we're going to actually calculate something. So before we do that, let's actually figure out what the electric field is for a point charge. Yeah, mathematical expression for it. Okay. So here's my little charge here. This is some plus Q. Now I want to call some distance here, R. And I want to find E here. You tell me how to find it. I'll give you a hint, you're pros at this. And just so you know, down, up, 116 equals y naught. And flat, 114 equals y naught. Boy, that changed my life. Good to know. Okay. Little humor. So, what's the electric field here?
It's leaving, so it's positive.
Okay, so how do you calculate electric field? What's the fundamental definition? Of this object on some little positive test charge little q over little q. Okay, so I'm going to put a plot so to do this. I come over here, I put my little positive test charge q here. And I ask, what is this force? So what is this force if I look at the magnitude that this q exerts on little q? I'll give you a hint you're frozen at this. This is R. What is the force between those 2 point charges?
Are you gonna use the equation force equals K Q1 Q2 divided by R squared? No?
Sounds perfect. And Q1 and Q2 are what in this case? Big Q and little q. Okay, you don't have kids most likely. You hear big Q, little q, what do you think of? Dr. Seuss. Big Q, little q, what begins with Q? The quick queen of Quincy and her quacking quackaroos. Okay, when you have kids and you're close to having kids and not having kids, you too will be able to quote and sing along with Dr. Seuss's alphabet book. Big A, little a, what begins with A? Oh no, big A, little a, what begins with A? Apple, Annie's something, A. I remember the Q. Big C, little c, what begins with C? Camels on the ceiling, C. Okay, well, okay, so K, big Q, little q over R squared. You have to chant it. You can't chant Dr. Seuss, you can't do anything. Okay, so what's the definition of the electric field? It's going to be this force over little q. What happens? Yeah, the little q's cancel here, and this just gives K, big Q over R squared. That's the electric field for a point charge. That's only for a point charge. Okay?
I'm just trying to understand how we went from over Q to over R squared.
Okay, so are you happy with this definition here?
Yeah.
Okay, so we're going to take this, put it in here. This will be big K, big Q, little q, okay, over R squared, over Q. Q's cancel, which is it. Make sense? Now, why do I mention this? Okay. One way to find the E field for a charged object is to treat the charged object as, what do you think we could treat it as? How many?
1%.
A whole bunch of point charges. So you can treat the object as a collection, as a large collection of point charges. And this is what I mean by this. So let's say here's an object here. We're going to put charge all over the thing. Now I want to find the E field here. Find E here. What would I treat this mess as being? A whole bunch of point charges. So I draw some tiny little point charge here. Here's a tiny point charge. How do I draw, what do I normally call a tiny charge in physics? Okay, the symbol wise. You put a delta. So this would be some little delta Q. Okay. And the distance from here to there would be R. And so it has some little tiny electric field here. That would be my tiny little electric field from this point charge here. The magnitude of this tiny little electric field would be K delta Q over R squared. If I then wanted the total electric field, what would I have to do?
Summation of all of them.
Exactly. I then have to put in this point charge over here. Find this electric, so I look at this one here. So that would be some new electric field going this way. I call it D here. I look at this one over here. This delta Q, I look at this guy, and then that'd be one. I'd have to sum up the contributions from all these little point charges. In terms of calculus, this is called integration. But it tells you something. How easy do you think this is to do? This is pathological. Even if you have a lot of calculus, this is still pathological. So this is very hard to do. So this procedure, although correct, is hard to do unless the geometry of the object is simple. And I want to show you one of the few cases you can actually do this without calculus. We're going to do calculus without doing calculus because it turns out it works out nice. Let's take one example where we can do this. So here's the XYZ plane. I'm going to have a ring here, a radius R. So this is a ring, a radius R, lying in the XY plane. So that would be one. Imagine my hand is the XY plane. Here's my ring. I'm putting it there as radius R. So this is what I'm looking at. And here's the z-axis when you have this. Okay? And what I'm going to do is I'm going to put positive charge on here. Positive charge over here. And I'm going to put it on uniformly. So my wedding ring here, I'm going to take positive charge. I'm going to go grab my little jar of a positive charge, put my knife in it. I'm going to uniformly spread this with positive charge. I'm going to put it in the XY plane. Okay? So the charge is uniformly distributed. The total charge is Q, and it is uniformly distributed. I have a point here, and this is Z. Okay, and we want to find E here. So we want to find the electric field along the axis here for a uniformly charged ring, a radius R. Let's do this. It's one of the few problems we can do. Okay, if you're in the engineering version of this course, we could do a couple more examples, but to be honest, even in the engineering course, you're really limited to what you can do. As it turns out, the calculus for this becomes pathological, really pathological, really, really fast. Okay, so you tell me what to do. What are we going to treat this ring as? What did we say? One way to find the electric field is to treat an object as a collection of point charges. So we're going to draw a little point charge on here. So treat the ring as a collection of point charges. And this needs a picture. So we're going to do that. So here's my here, and I'm going to look at right over here. Here's my little point charge, delta Q. And here's that little point. And from here to there, this is R. So how does the electric field go here due to this little point charge? Well, the charges that have an electric field around it. So here's my ring. I'm looking at this little section. Here's my little DQ. So I want the electric field here due to this little point charge. How would that have to look? Well, this is positive. This is just a point in space. How do we say, if you have a point charge, how do electric fields look for point charges? They come outward like a porcupine, right? And what's the magnitude of an electric field for a point charge? This stuff is hard when you're first learning it. So you're going to have to be patient. It's very hard. Yeah, it's going to be the KQ over R squared, and the Q in this case is delta R. So I'm going to have the little electric field here. I'll call this delta E. The magnitude of this is going to have to be K. The point charge here, delta Q, over R squared. If I want the total electric field at the spot, then what do I have to do? I have to add up all the little, I have to treat this ring as a whole bunch of little point charges all the way along here. I have to add up the contributions from all these little point charges. And that'll be my total electric field at that spot. Okay? But something happens. Let's look at this one over here. Let's look at this delta Q. This delta Q is 180 degrees from the first delta Q. Meaning from this guy. It's 180 degrees away. How does the electric field look at this spot due to our little friend here? It goes like this. This is this delta E. What's going to happen at this spot? They're vectors. What are the vectors going to do? Add. So you're going to have this component, and this component, and this component, and this component. Something happens. By symmetry. You have these horizontal components. Okay, they're wide here, but anywhere along here, they're just going to be horizontal. What will these components here always do? By symmetry. These will always cancel. So the horizontal components cancel. But I'm left, so we don't have to worry about them. So what that means that if I look at this ring here, I'm sorry, use calculus there. We call this delta EZ here like this. This is the delta EZ component. Only this component survives. Does this make sense? So only the delta EZ component survives. So let's call this theta. Tell me what this delta EZ is. From this picture here. You done this first semester?
You just mean like sine and theta?
Yes. It's going to be what times sine of theta?
The magnitude.
Yes, you mean the magnitude of this guy. Perfect. I'm just sine of theta. Well, what is this magnitude given by? What did we say is the electric field for a point charge? Okay. Delta Q over that little r squared. So this is delta EZ. Okay, delta Q over r squared sine of theta. This is R, this is big R, and this is Z. What is this little r given by?
If we knew the other values, couldn't we just do like that right here?
That's exactly what you do. So what is this? This little z, this little r would be what?
Square root of r is z squared.
Big R squared plus c squared. So that's what this r is. Where else is theta here? This is also theta. Yeah, this angle, this angle, this angle. If I draw this a little more straight, I have a little curve like this. It's a little more obvious. Right? So what is the sine theta here? If you look at this triangle.
Z over this square root of r z squared.
0 and a little r. So we put this in here. So this will give us k delta q z over little r over r squared, or k delta q z over r cubed over r cubed. But wait, we know what the little r is. The r is square root of big R squared plus c squared. This tells me delta EZ equals K delta Q Z over. What's another way of writing something to the square root? Same as raising it to the 1/2 power. Right, so this is really R to the R squared plus C squared 1/2 power. So if I put this in here, this gives me R squared plus C squared to the 3/2 power, because it's coming in cubed. Right? Because this little R here is to the 1/2 power, so if you cube it, you get it to the 3/2 power. Now, if we want the total electric field from that ring, how do we have to do that? We have to add up all the little contributions along here. So we have to sum of all these little delta EZs. We're doing the sum along the ring. So this gives me that sum of K delta Q, hell's almost over. Of K delta QZ over R squared plus Z squared to the 3s power. What are the constant terms here? Okay, is constant. Is it Z constant? Yes. What about the big R squared plus Z squared? They're constant, so you can pull those all out. We're summing the delta Q, so I can't pull that out. You tell me what that is. What is the sum of all the delta Q's on the ring? Right, so I take this delta Q, and I add it to this delta Q, plus this delta Q, plus this delta Q, plus this delta Q. I add them up along the entire ring. What does that equal? This is the total charge of the ring. Which we just found big Q. So this gives me KQZ over R squared plus Z squared to the 3s power. And that's the electric field. If you have a uniformly charged ring like this, you take a ring, put charge uniformly on it like that. If I want the electric field anywhere along the Z axis, it's given by this. And okay, now the next statement is going to sound stupid, but it's true. The only reason we can do this is because this is an easy problem. You look at this for the first time and you think there wasn't one damn thing easy about this. And that's true when you first see it. But it's one of the few problems you can actually do. Okay, now, again, if you have calculus, you can do a handful more. But to be honest, this would even be hard for the engineers to do. Okay? This is involved. Yes? Something like this, I think, would be fair game. But this would be about as hard as it would get. And also, it's the only one we can do with this signature. We're going to find some other ones, but we need something else. We're going to have Gauss's law. Gauss's law, which we're going to do next, comes with a price. It's going to be easy to do, but it comes with a really tricky conceptual. It's a very abstract way of thinking. And that's going to be the price we pay, abstraction. Okay, any questions to this? This is hard. Why would we care about the electric field here? If I did the electric field along this, so here's if I charge on this, I put it here, and I don't know the electric field anywhere along here, I could now put in a charge, a little q, anywhere along the z-axis. And what would the force have to be in that little q if I put it on the z-axis? So let's say I have this here. I put a tiny little charge here, and I want the F on this. What would be the force? How's the electric field and the force related? Remember this E equals F over Q. If I know the electric field, if I want to pull that out of my point charge Q, that gives me my F. So I know that this has to be Z. And we're going to use this later on. I'm going to show you how 3 chemistry device works. Okay, so if you're a chemist, you use 3 things a lot. You use a mass spectrometer, you use NMR, and then you also use a gas chromatograph. I'm going to explain how each of those work. Okay? And this is going to be part of what we need for a mass spectrometer. It's tucked away in a very special place in the mass spectrometer. This guy right here. Well, we're not there yet. Questions? Okay, this is real. If you looked at this and said, oh no, I'm done, you know, I might as well leave the class, I'm going to fail. No, you're not. Okay. This is about one of the hardest things we do. Okay? And at this level, it's about the only problem without calculus. This is only one of the few problems we can do. We actually did calculus here without doing calculus. You don't know that. But we did calculus without doing calculus. Questions? So what did we do? We looked at basically, you know, we have our definition of electric field, and we want to start putting electric charge on things, and we want to start asking, what is the electric field for that charged object? The first charged object we looked at was the uniformly charged ring. Okay, I think I killed everyone today. A little bit.
It's just in the Z plane, right? There's
Exactly.
2 others, right?
Well, okay. Just as you go here, you can say, well, I want the electric field here. You leave the z-axis. The complexity that you get for going off that z-axis is phenomenal. It's absolutely
So
phenomenal.
we don't know.
Not in this course. In fact, you have to take the advanced course to find out how to go off axis. You go off axis, it's a beautiful calculation, but it's it has an edge to it. All this stuff here, if you take a problem and tweak it a little bit, it just out there becomes harder. It becomes almost exponentially harder. There's a couple little set problems you can do, and any tweak on those, the complexity is just phenomenal. If you want to scare a physicist, you don't give them quantum mechanics. Absolutely no physicist is scared by quantum mechanics. So quantum mechanics, believe me, is not hard. It's actually quite straightforward. If you want to scare a physicist, what you do is you bring them electricity and magnetism problems. In particular, there's a book called Jackson, which is a standard graduate test. You bring them a book, you say, oh, I've been reading Jackson's classical electricity and magnetism. Now I have a question on here. Could you help me with the Jackson problem? I can guarantee you that physicist is going to come up with some excuse of why they have to leave right away. I have to go by. You will scare the hell out of them because that'll bring back such bad memories dealing with that book. The problems are hellacious. You just have problems which take an ungodly number of pages to get done. They're pathological. Okay? We're not doing those. This will be the hardest we get here. Okay? Have a good day. And also, this is an on the test on Thursday.
Have a good day.
Thank you, Early. So Sandra, I will, no more Sandra.